One day we're gonna live in Paris, I promise.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. Now we move on to an introduction to aromaticity. And so I want to start out with a historical background to benzene because it's pretty interesting. So in London, 1825, street lamps were fueled by gas derived from whale and cod oils. But then liquid benzene was condensed in pipes, but no one knew what the structure was. So this was actually analyzed by Michael Faraday, this guy right here, in 1825. And he used vapor density experiments and revealed the formula of C6H6, which is the formula of benzene that we know today. But at this point, they didn't know what the structure looked like at all. All they knew was it was C6H6 with a molecular weight of 78. However, benzene is pretty inert and stable at room temperature and more resistant to catalytic hydrogenation that we talked about before than related substances. So he was really confused as to what this structure looked like. And benzene is not like other substances that have similar formulas. So another really complicated thing is that there's 328 isomers of C6H6 that are possible. That is a lot of things that everyone had to go through to figure out the actual structure of benzene. So this problem remained unsolved for 40 years until two key ideas were formulated by these two gentlemen. So in 1857, Frederick Kukule suggested that carbon can form 4 bonds, like so. And in 1864, Alexander Crum-Brown suggested that carbon can also form multiple bonds, like what we know today with the double bonds and also the triple bonds. And this was not known before 1864, which is kind of crazy, right? So at this point, with these two clues, Frederick Kukule actually figured out the benzene structure, which we know today, in a dream. Sounds kind of crazy, and I wish I could figure out all the chemistry problems in my dreams, but what he came up with was this benzene that they called Kukule benzene for a while. But Kukule had a lot of problems when he first saw this benzene structure. Well, first off, there was the isomer problem. This is something that I talked about in the isomer chapter, which you guys should be familiar with now, and I told you guys that the reason why isomers exist is because of the bond length problem. The carbon-carbon single bond is greater than the carbon-carbon double bond, right? And so the Kukule structure that he initially drew had different lengths, so it was kind of distorted like this, where the single bonds were longer and the double bonds were shorter. And so it looked something like this, and it was distorted. There we go. Based on the fact that carbon-carbon single bonds are longer, carbon-carbon double bonds are shorter. And so Kukule's structure could not be accurate because this was not possible. And so Kukule actually came up with a solution to the isomer problem by saying that isomers in very fast equilibrium switch back and forth from the other side structure. So like this. So now we have the double bond here, here, and here. Sorry, these distorted structures are pretty hard to draw. And instead of the isomers, he was thinking that there was fast equilibrium that allowed these to shift back and forth. However, separate structures could not be isolated or detected, and regardless of the equilibrium rate, the carbon-carbon double bond was always present. So the second problem that Kukule encountered when trying to figure out the structure of his benzene molecule was when he looked at reactions. So when you have a very straightforward alkene reaction like this, and you react this with Br2, this is a typical alkene reaction, you end up with bromine on either side of the double bond. like so. And this is a very typical addition reaction. And so he predicted that similar functional groups would have similar reactions. But in fact, when he reacted the benzene molecule with Br2, he got no reaction. And a catalyst was required. And this means that benzene is even less reactive than an alkene, and no substitution or addition reaction occurs. And so you had to think about this real hard and figure out what the problem was. And so in order to revise Kukulay's structure to actually have properties that are consistent with all the different things that he saw, he thought of resonance. And so Kukulay's benzenes are isomers and have resonance contributors. And so we talked about this in our resonance chapter, where these isomers have no discrete existence, and it just has this resonance hybrid structure, which is either drawn like this, or it's also drawn like this, with the dotted lines. And so he predicted that now all the carbon-carbon bonds are of equal length, which was actually verified by X-ray diffraction in 1928 by Kathleen Lonsdale. So what's so special about Kukulay's benzene? Well, first of all, it took forever to figure out the actual structure, but it can actually explain its special stability via resonance, via conjugation, and we can actually measure this special stability via catalytic hydrogenation. This special benzene stability is what we call aromaticity. And so why is it called aromaticity? Well, the first molecules known to contain benzene rings had pleasant aromas, hence aromatic. But not all benzene-containing molecules actually have pleasant odors, but that's where this name actually started. And there's other aromatic structures in addition to benzenes. These are a couple of examples. But now I'm going to give you an actual definition of what aromaticity means. And this is the special stability possessed by a molecule which has 4n plus 2, where n is an integer, pi electrons contained within a closed loop of adjacent, parallel, overlapping p orbitals. And so I'm going to show you now how to predict aromaticity. And there's 3 requirements that are basic in order to figure out whether something is aromatic or not. So the first thing that's required is a closed loop of p orbitals. And so this means that you have a loop of sp2 or sp atoms, like a benzene molecule. The second requirement is that the atoms of the closed loop must be planar, so that you have the p orbital overlap. And to override planarity and aromaticity, strain must be severe. And number 3, the closed loop must contain 2, 6, 10, 14 pi electrons. And this is called Huckel's rule. And so this series is described by the formula that I gave before, which is 4n plus 2 is the number of pi electrons, where n is an integer. And the most common one is having 6 pi electrons, which is what you see in benzene. You have 2, 4, and 6 pi electrons. So one thing that's really important when you predict aromaticity is knowing how much strain is too much strain. So you basically have to balance the stabilization from aromaticity with the destabilization from the strain. So I'm going to write that right here for you guys to keep in mind when you predict aromaticity. And this has to weigh with the destabilization from strain.